stress Z of element A. So this is equal to minus 100 times 10 to the power 3 divided by 5310 times 10 to the power minus 6 minus by my, which is equal to 9600, multiplied by x, which is 8 times 10 to the power minus 3, divided by izz, which is equal to 40.9. And then we have plus mx, which is equal to 22750, multiplied by y, which is equal to 0.1025, and then divide by ixx, which is equal to oh, I got the other one wrong. So this is iyy. So iyy is 9.01. Ixx is then 40.9 times 10 to the power minus 6. So now you compute your values. So you got 100 power 3, 5310 power minus 6. So you have 18.832 minus, right, times 10 to the power 6, minus by 9600 times by 8 power minus 3 divided by 9.01 power minus 6. So you got 8.524 times 10 to the power 6 plus 22750 times by 0.1025 divided by 40.9 power minus 6, 57.014 times 10 to the power 6. Okay, I'm calculating again. 18.832, that's good. Then 9600 times by 8 power minus 3 divided by 9.01 power minus 6. 8.524, that's good. 22750 times 0.1025 divided by 40.9 power minus 6. 57.014. Okay, so this is great. So this will be equal to minus 18.832 minus 8.524 plus by 57.014 is equal to 29.658 times 10 to the power 6 Pascal, and it's in positive. Minus 8.524. Yep, 29.6. Okay. So the normal stress is straight. Now let's focus on the shearing stress now. Okay. The shearing stress of element A. It's not difficult. You guys have done it before. Now the different thing is we have two force component. Okay. So we are aware that for element A is shear ZX. Okay. So shear ZX so we have two force components, right? We have Vy over Ixx Qx over T. And then we have tongue twister, Vx over Iyy Qy over T. Okay. And then it's up to you. So from here, I look at over here. Okay, so I'm going to declare, okay, I'm going to declare what is going towards the shear flow towards the right hand side is going to be positive. Okay, so if we look at Vy, it's going to be positive. And if you're going to look due to Vx, okay, so due to Vx is down here, right? Due to Vx, right? So this is Vx. It's going towards the left. So I'm going to call this negative. So let's gather our values again. So we know that Vy is equal to what? So we calculated our Vy. Vy is equal to 25 times 10 to the power 3. And then we also know that our Vx, right? Vx is equal to what? Vx is equal to 16 times 10 to the power 3. Okay. So now let's look at this diagram over here. For either one would be fine. Or let's deal with let me see what did I put first. I put Vy. So let's deal with Vy first. So you put in your Vy. Okay. So this is by consider your Vy. Okay. So we know, right? This is the, so let's consider Vy. Right? So we know that this is our thickness. So for Vy, the thickness is equal to what? So that is the thickness, right? You can see that this is the thickness. Remember, the thickness in thin wall analysis is perpendicular to the direction of the shear flow. Yes or no? Right? So Vy, so we need to consider Tf divided by 2. So 41.7. So we need to consider Tf. Okay, so don't need to divide by 2. Okay, so the thickness is 11.8 times 10 to the power minus 3. Okay, so this is 11.8 times 10 to the power minus 3 meters. So we do know Vy. So the next thing again is we're going to calculate Qx. Right? So to calculate Qx, we know that we have to determine up to this point down here for element A. So it is this area that we're going to consider. Okay. So that distance over there, right? So this is equal to Qx. So width, depth, y bar, right? So this is equal to the width. As we know, the width from the terminal to point A is 75. Okay. So it's equal to 0.075. The depth is going to be your what? The depth is going to be the thickness of the flange. So thickness of the flange, which is TF over here, that is equal to 11.8. Okay, so 11.8 times 10 to the power minus 3. And then the y bar, right? The y bar, so the y bar is, I'm going to sketch over here. So this is our y bar, right? Up to this center over here. So it's d divided by 2, right? So it's d divided by 2. So we go back here. The d is 0.205 divided by 2, right? And then minus 11.8 times by 10 minus 3, and then the whole thing divided by 2, right? Because the thickness of the flange is equal to 11.8. Okay, so from here, you have 0.205 divided by 2 minus 11.8, 0.8 power minus 3, divided by 2, times by 11.8 power minus 3, times by 0.075 is equal to 85.491 times 10 to the power minus 6 meter cube. Let me do it again. 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.075, 75 millimeters, 85.491. Okay. So if we look at the first part of the formula, we have this, we have this, we have this, and we have this, right? We know Vy, we know T, Izz, we know one. Now we know our Qz. Okay. So that is considered our Vy. Okay. Then we are going to consider we're going to consider our Vx. Okay. So again, you come over here, you copy what we have over here. Come on. I'm just going to grab the whole thing and I'm going to put here, do some tidying up, some things we don't need. Okay. So now we consider our Vx now. Okay. And you realize that the second moment of area, the first moment of area is not the same. Okay, I'm going to put down here. Okay. Right. So Vx, we know. Okay. So the next thing is the thickness is still the same. Right. So this is still the thickness. So from here, you know that the thickness is equal to still the same like before, 11.8 times 10 to the power minus 3 meters, right? No doubt, one is known as Vy, the other one is known as Vx, okay? But the thickness is still perpendicular to the direction of the shear flow, and that is still 11.8, okay? So now we have to take a Qy, first moment of area by the y. So this is where you have to be careful. So this is with depth now become x bar. Qy, yeah, x bar. Okay, so what do I mean? So now we know that we want to Qy. So now this is our width. This now becomes our what? Our depth. X direction is in this direction. That's our x direction. Okay. Right. So from here, we look at our width is equal to 11.8 times 10 to the power minus 3. The depth is still 75 times 10 to the power minus 3. Okay. Now the y bar, so if this, I'm going to get rid of the arrows over here. And this is our element A, right? So the y, the area to consider is this area over here. So what we need to do is we have to find, okay, we have to determine, right? What is this value over here, which is our x bar. Okay, that is our x bar. So we can find this by knowing this distance over here. So we do know that the distance from here to here, we know. And then we also know the distance from here to here, right? So the distance from there, so is BF divided by 2. So it's your B F. So 166 divided by 2. So I'll write down here the direction. So this is 0.166 divided by 2. And this distance over here is equal to 0.075 divided by 2. Then you have your what? You have your x bar, okay? So from here, you can write down as 0.166 divided by 2, right? And then minus by 0.075 divided by 2. You have to be really, really careful with this, okay? What you can see is if you take from Qx, right, Qy, no doubt the first two terms, the values, the magnitude are the same, but what you minus off is very different, okay? So this will be equal to 0.166 divided by 2 minus by 0.075 divided by 2, okay? 10 by 75 power minus 3 times by 11.8 power minus 3 is equal to 40.2675 times 10 to the power minus 6 meter cube. Let me do it again. 0.166 divided by 2 minus by 0.075 divided by 2 times by 75 power minus 3 times by 11.8 power minus 3. Yep, 40.2675. Okay, so now we have everything now. Okay. Okay. So I'm not going to go for the next page because since all the values are here, we are going to delete on this page over here. Okay. So we know that we're going to put this formula into here. Okay. So we can see that shear xz or zx so this is equal to Vy. So I'm going to call it positive 25 times 10 to the power 3 multiplied by 85.491. So here z x at a. So this is equal to